matrix polynomial concentration and Lasserre lower bounds for planted Clique. Raghu will begin.
Thanks, Prasad. Thanks for inviting me here. And I'm also really glad that there's a lot of horizontal space because I can finally fit the title of the talk on the board. So of the paper. The paper title is Association Schemes, Non-Commutative Polynomial Concentration, and Lasserre lower bounds for planted Clique. And I'll talk about each of these pieces. These two will be our tools to solve this problem. Okay? But the tools itself, the way we use it and the things we develop there might be useful elsewhere. So let me start with this classical question. And the main object of study here is a random graph drawn from the distribution g n half. So you have a graph drawn from g n half, and we are really interested in largest clique. So how big is the largest clique in G? And it's an easy exercise to show that the largest clique is roughly exactly something like this. 2 times log m plus some little over 1 terms. And what we would like to understand is if we can find large cliques. So can we find large cliques from random graphs drawn from g n half? And the simple algorithm where you basically just count the degrees and so on says that we can find cliques of size log 2 base n, log n base 2. Okay. And this problem has received a lot of attention, and in fact Carp in 76 asked if can find a clique of size 1 plus epsilon times log n. Can you find a clique of size 1.1 times log n base 2 for a random graph with high probability in polynomial running time? And this has been around for a long time. We haven't made much progress on this, but what can we say about it? Well, there is a simple algorithm which runs in quasi-polynomial time. You just look at all possible log n sizes, and that gives you an algorithm. So can solve n to the O of log n time. And beating this has been a challenge. It's also been kind of posited as a hard computational problem used for building certain crypto systems and so on and so forth. And because this problem has been so hard, a very nice relaxation of the problem, which is interesting by itself, was suggested by independently by Jerome Kuchera. So what's the relaxation? So we start with the random graph as here, but we now plant a big clique inside the graph. So this is the planted clique problem. So you have a parameter t, which is typically much bigger than log n, and let me write it down. We are given a graph g from g n half. Let me just denote it as g n half t, meaning you just draw a graph from g n half and then add a clique. The largest clique in these graphs will with very high probability be exactly t, and the question is, can you find large cliques now? And Ideally, you would just like to find the planted clique, but even just finding large cliques is actually hard. I mean, we don't know how to do that. So what do we know about this problem? Kuchera himself showed that you can solve the problem if t is roughly square root n log n. T is bigger than square root n log n, then you can just count the degrees, and one of the vertices has such large degrees, so you can find the clique. And Alon, Kribilevich, Sudakov, 98 gave a spectral algorithm which solves the problem for t which is omega of root n. And this has been the state of affairs since. And the main challenge has been to break the root n barrier. Can you find a large clique if I plant a clique of size n to the 0.49, 0.499 or anything like that, where you beat the square root n by an exponent? And once again, this has received a lot of attention, and we don't know much in terms of positive results, but there's been a lot of work in trying to understand what algorithms, what classes of algorithms can or cannot solve this problem. So this is in the context of lower bounds for this problem. So, this is average case, so you have to be, so we don't have as nice a theory for average case hard problems in terms of reductions and so on, but in some sense it stands its own league, I think, because of this n to the log n trivial algorithm. So the scale is different. Yeah, right. And in fact, I think this problem is kind of, it's not just a standalone problem of curiosity. In print,
So is it possible to plant a clique of size n to the 1/100, and this is random gn 1/2?
So there are no reductions like that I know of. And I think getting such reductions or formulating the right conjectures would be great, because the current techniques don't allow for that. The theory would be nice, like something like that would be great. I think Fege has some reductions along those lines, but not for this problem, from some other problems. So what we'll study here is lower bounds for this problem in restricted computational models, but these restrictions are themselves quite natural in the setting we are looking at.
So there is even effort to beat the constant in front of root n, right?
So there you're really interested in like linear time versus polynomial time. So what they show is I can solve the problem for t is omega of t is epsilon times root n in time n to the o of epsilon, I think. Oh, sorry, 1 over epsilon. So you can keep improving this, but then you lose in the polynomial time running time. So lower bounds. So the first lower bound was actually from the paper of Jerome that introduced this problem. So he showed that MC-MC algorithms, a broad class of MC-MC algorithms that he formally defines, but I don't want to go into here, cannot solve the problem for t less than root n. This t is n to the 0.49. This cannot solve the problem. These algorithms cannot solve the problem. And we'll see why root n occurs as a natural barrier in a few when we look at the proof, but that's what happens. And
Does Aron's algorithm fit within the MCMC framework?
no, I don't think so, because it's spectral and it's a different class. Yeah. And in terms of positive results, there's a very nice paper of Fege and Rodgamer. So what they actually show is not just that can solve this problem, but you can also solve stronger problem, but still for t is root n. I won't define what the stronger problem is. Basically, there after adding this planted clique, you can delete some edges and you can still work, or add some edges. So what they showed is that the Lowas-Schreiber LS+ hierarchy. So because it's a combinatorial optimization problem, one of the most powerful techniques we have for solving such questions is our hierarchies. So you start with the base problem, formulate it as a convex optimization problem, and then you consider relaxations of it, which come from the lift and project methods. And what they showed is that R rounds of LS+ solves for t which is root n by 2 to the r. So I'll be skipping all constant factors, but that's not important for us. And this is what they showed. If you look at R rounds of Lowas-Schreiber hierarchy, the semi-definite version, then you can solve the problem for t which is roughly square root n by 2 to the r. And again, this matches the lower bound we had, the algorithm we had earlier, if you want to beat root n by a polynomial factor, because you have to go up till r which is some log n. And the important thing to keep in mind, which is that this can be done in n to the o of r time. So if you consider r round relaxation, then you can solve the problem in n to the o of r time. So I won't define what this hierarchy is, but we'll consider I'll define what strengthening of this hierarchy that we'll study later on. So that's great, but in a follow-up paper, Fege and Krautgamer again showed that this hierarchy, which is a very powerful class of algorithms, cannot do better. So they showed that LS+ after R rounds not solve for t which is much less than square. So you really have to go up to log n rounds if you want to beat root n. And what we'll consider here today is a much stronger class of semi-definite relaxations, which is the Lasserre hierarchy, and we show an analogous result there, a lower bound for that hierarchy. This is the main theorem of this talk. Again, I'll define this hierarchy in a few slides, in a few minutes, but it's the most powerful class of semi-definite relaxations we know. So there are various names of this. Let me just write them down. Sum of squares and cannot solve for t, which is, it's not exactly square root n by 2 to the r, but t which is root n by log n raised to 1. So it's an exponent of r squared. So what, question? So what this means is that you have to at least go up to square root log n rounds if you want to beat root n. And the upper bound is still the same, so there's a gap in the lower bound and the upper bound. But it at least says that you cannot get a polynomial time algorithm just by looking at Lasserre hierarchy. Okay.
I mean, it's arguable if it really implies that, because there are several algorithms now where you don't need to solve, don't need n to the order r time. You can solve it in order r time, poly n time.
2 to the order, yeah.
It depends on, not all
Yeah.
algorithms,
But you could say the same thing for LS plus then, right? So that's a different ball game.
So I don't understand. So what's wrong with taking R as constant if you're beating root n?
So you cannot solve the problem for, if you take R to be, you're beating root n, you want to beat it by n to the 0.49 or something.
I mean,
I think you can.
Little o of root n, at the moment we still don't have a polynomial time algorithm for little o of root n, right?
Yeah, you are right. You're right. But I think this lower bound, the log n, is kind of extraneous. The most interesting setting is if you want to get n to the 0.49. It's somewhat of an artifact of the analysis, I would say. So if I were to venture a guess, I would. So the right answer should be this, but some people believe it's 2 to the r squared. So, and why is this hierarchy? That it's a completely. I think it's a completely different beast from LS plus hierarchy, and this has been of considerable attention in the past few years because this hierarchy is of imminent threat to many central questions. In a recent work, Barak et al. 2012 showed that there exists So we had a class of hard instances for the unigames conjecture and related problems, which were hard for LS plus, Shirali-Adams plus, and all of these weaker SDP hierarchies. But this hierarchy actually can solve all of those hard problems, all of those hard instances. It can solve gap instances. For unique games, max cut, process cut, and related problems. So this hierarchy is genuinely more powerful than LS plus and Shirali-Adams plus and all the other hierarchies. So coming up with lower bounds for this hierarchy is more of an evidence for the hardness of the problem, I think. So let me now talk about how we prove this theorem, and I'll just get.
Any previous lower bound for the Lasserre?
Oh yeah, there are. Yeah, I'll get to them in a bit, but let me just jump ahead and say that now. So. In terms of lower bounds, so there's a work of Grigoria which introduces positive Stellensas framework from around there. So this work is very powerful because it proved lower bounds for the hierarchy even before it was defined. And basically for knapsack and random k-lin, 3-sat, and some of these results, especially the ones for 3-sat and k-lin, were rediscovered by Schoenebeck in 2008. And once you have this kind of base lower bounds, you can use these and combine with known reductions to get further lower bounds. And this was, I think, Tulsiani used these plus reductions to get lower bounds for Max Clique and others. So you might ask, we already have a Lasserre lower bound for Max Clique, but the problem is that, the lower bound instance here is worst case. So you start with a random 3 set and run it through your favorite NP hardness reduction. You don't understand what distribution of instances you're going to get. But we are really interested in a natural distribution like G and half T, and so on. So that's why we kind of have to start from, in some sense, start from scratch. We'll use the techniques, but we have to cannot use these lower bounds as a black box. So in the remaining 20 minutes, let me spend 5 minutes here, 5 minutes here, and 10 minutes on how the actual lower bound goes. Okay. So association schemes, some of you might have seen this before. So these are classical objects in coding theory, combinatorics, and I think coding theory and combinatorics mainly, which have been studied a lot. And here I'll specifically look at Johnson's scheme. Johnson's scheme. And so what Johnson's scheme is, it is a vector space of matrices with a certain property. So let me define how what this space is. It's a space of matrices, and the rows are indexed by subsets of size R of, you have an n element set, and the rows are indexed by subsets of size R, and the columns also by, let me just write this as, and you have a function mu which from 0, 1 through 2R, let's say, to reals. And given this function, you can define a matrix here as follows. So this is mu. If I take a specific subset I and a specific subset j, then the ijth entry is mu of the size of the union. Okay? So the ijth entry only depends on the size of the union, but not on the specific sets. So the space of all these matrices is the Johnson scheme. Okay. So these are huge matrices, but the number of free parameters here is very small. You have only 2R parameters. Okay.
So
and
it's arbitrary, magnitude R?
it could be negative, anything. And because you want a vector space in the end. So. And this set of matrices has some really nice properties, and the most important of them, which we will use throughout, is that all mu commute. You can work this out just by some simple calculations, but this is very important. And if you have a bunch of matrices which all commute, what do we know about them? Then you can diagonalize them simultaneously, and that means there exist eigenspaces. There exist some vector spaces which are simultaneously eigenspaces for all the matrices in this class. So, and not only that, coding theorists and combinatorialists have characterized completely what these eigenspaces are. So we know what the eigenspaces are. And because of this, there is an analog, at least in philosophy, of Fourier transform for these matrices. Let me put this in quotes. We can do some kind of Fourier transform for MUs. And we also know what eigenvalues are from mu. So if you give me a mu, I can write some expressions involving some binomial coefficients which will tell me exactly what the eigenvalues are. And finally, this was something new which we had to kind of develop somewhat on our own. You can also understand which matrices in this class are positive semi-definite, and that will be very important for us. This is not a characterization, but it's a very useful way of proving things are positive semi-definite and so on. And we will use this property and this property in our analysis. So that's all I'll say about association schemes. And now let me talk about the second tool, which is non-commutative or matrix polynomial concentration inequalities. Okay. So let me just first talk about polynomial concentration inequalities. So what's the setup here? Let's say you have epsilon which is chosen uniformly at random from 1 minus 1 to the n. So random plus 1 minus 1 string. And I have a polynomial p from Rn to R. Let's say the constants term, no constant term. And what we are interested in is to show some kind of concentration for the polynomial p evaluated at a random plus or minus 1 string. So let me define the error function t as probability that p of x, p of epsilon is t times some parameter. So what should I put in here? It should be the standard deviation of the polynomial. So that's how you should scale things, and I'll write this as the variance of p raised to the power half. And the variance of p or any polynomial is just the expectation of so this is all standard.
Oh, there's no constant.
We write this as the max so this ideally this probability should be small, so I'm going to look at and what do we know about it? Let's look at some simple examples. The classical Chernoff bound says that if your polynomial, let me write it down here, something, then you get the following error function. So if p is just summation ai epsilon I, so that's a linear function, then the deviation you get is basically exponential in minus t squared. You get sub-Gaussian concentration, and this has been known for a long time. There is another inequality which comes from hypercontractivity, that if p is a degree d polynomial, so you have a degree d polynomial, then the right concentration is So it's exponential, but you lose a factor of d in the exponent of t. So if you put d equals 1, you just record the old result.
So the variance of the polynomial doesn't appear in the bound?
No, it doesn't, yeah. Because you kind of normalize by it. And there's a different generalization of this, which is somewhat recent, but it's also very powerful. This is matrix polynomials. So let me write this result. This is due to Oliveira from 2008. So instead of looking at just a linear function on epsilon i's, I'm going to take a sum of random matrices where the coefficients are these epsilon i's.
There has to be some normalization you haven't shown, even for the Chernoff problem.
So the way I define the error function already is removing the
I see. Okay,
yeah.
sorry.
So now I want to make similar statements, but where my polynomial is takes matrix value. So think of AI as a d by d symmetric matrix. Okay, and now let me just remove this absolute value here. It's somewhat annoying. So. But now it's a little tricky. What should the variance be, and what should this inequality mean? Well, it's natural to guess what the inequality should mean, and so greater than for matrices is in the positive semi-definite ordering. So the definition of the variance is still the same. It's just the expectation of p squared. And now the variance will be a d by d matrix, which is positive semi-definite. Okay. And what we want is that the polynomial be greater than the variance times some factor t in the positive semi-definite ordering.
What's the root?
It's the square root in the usual sense, because its variance is a positive semi-definite matrix. You can look at its square root.
So you get positive semi-definite, not spectral norm inequality.
So the original inequalities were stated in terms of spectral norm, but you can easily prove the positive semi-definite statement from the spectral norm version. It's easy to go from one to the other. And for us, it will be important that we're working the positive semi-definite ordering, and it's kind of more natural, I think.
It's a weaker statement when you say positive semi-definite.
No, it's
No, not
spectral norm. Yeah. Spectral norm is weaker, but it's an easy reduction. So what do we know here? This is shown recently, and the error function now is the same as before almost, but you lose a factor which is the dimension of the matrix. Okay, so if it's linear, you get d times exponential and minus d squared, and this factor of the dimension is necessary in general, and it's an important factor. So if I show you these three things, then the next question is, or should be, what happens if P is a matrix polynomial? Okay. So what if P is So what happens now? And turns out that in our proof we actually need such a tail bound, and this is what we show. So this is oh, I forgot to mention this. Don't tell Avi, but this is joint work with Avi Vigderson. So this is
He's watching you now.
We shouldn't tell him it's a joint walk with
Real
him.
time.
So what we get is, so if you kind of by interpolation, you should lose this factor of d from the linear case, and you should you have this. So kind of that's what we get. But there's a loss that we have, and this is n to the d. So the factor of dimension and this exponential minus t to the 2 over d, that is necessary just from these two, this and this. But we have an extraneous factor of n to the d, which we don't think is necessary, but our current proof does not show that. And for us, it does not matter because the dimension itself is of the same order. So you're not losing much in the tail bound for us. But ideally, it should not be there.
You are
And-
not assuming that the matrix is commute. So
No, no,
A
no.
sub I is really
Yeah.
an ordered thing.
Yeah. If the matrices commute, then you can probably do some other stuff. And there's a rich history behind even this linear case. The one I stated is due to is formulated like this by Oliveira, but there is work in Banach space theory about non-commutative Khinchin inequalities, and you can deduce these from there, and that's where we have the term non-commutative here. So in the remaining 5 minutes, let me just say how. Let me just define Lasserre hierarchy and say how these things appear. So the formulation of Lasserre hierarchy that I'll use is the positive Sternzach framework. It's easier to describe. And the starting point for that is the fundamental theorem of algebraic geometry, which is Hilbert's null-Sternzach. So what does Hilbert's null-Sternzach say? So it says if I have some system of polynomial equations, let's say these are when is this system of equations infeasible? It is infeasible if and only if the ideal.
The real terms or the complex terms?
Oh, sorry, complex numbers. Yeah, it's important. So when is the system infeasible? Infeasible if and only if the ideal of these polynomials contains if and only if there exist polynomials gi's such that if you look at the sum fi gi, you get 1. Okay, and this immediately implies infeasibility, and the converse is the real part of the theorem. This is great, but what if I put Rn here? So now I'm only looking for real solutions, which is often the case for us. And now this statement no longer holds. You can look at the polynomial x squared plus 1 equals 0. That has no solutions, but you cannot generate 1 from that ideal. And there's a rich theory called real algebraic geometry, which says essentially that this is the only exception you can have. These are the only polynomials which violate this equality. This is positive. So the system is infeasible if and only if the ideal contains a polynomial which looks like 1 plus a sum of squares of other polynomials. Okay? And once again, if you have such an identity, it is easy to show infeasibility. Okay? So this is great, but if you want to use this as some kind of algorithm or a certification for infeasibility, it's not so nice because these polynomials, there's no bound on the degree or the size. And what Grigoriev and Volobchow suggested was the following. The let me abbreviate this as PS, our proof system. So you want to prove the system is infeasible, but now you look for the same identities like here, but you limit the degrees of the polynomials. Okay?
This is the GI and the HI, no?
Fi times gi. It's just easier to write it this way. Okay? So all the polynomials in the identity should have degree less than or equal to 2r. Okay? And this is the proof system. And this exactly,
Not the number of H's.
there's no bound. So you can say that it's at most n to the r or something, but we don't care about that much. And they did this in 2001, and as it turns out, this is exactly or more or less the same as Lasserre R-round Lasserre relaxations. Okay. And this is the framework we look at now. So this is the same as showing Lasserre lower bounds or getting Lasserre algorithms.
That's for a general class of problems or just for Clique?
For a general class of problems. There are some technical conditions that this FIs must satisfy, like they have to be bounded or some such, but for us, those conditions always hold, and there this is just equivalent. And so let's see what this system of equations is and how we can construct such, show the non-existence of such identities for Clique. Okay. So the equations for cliques are quite natural. So you have a graph G, and let's say a parameter K. So you have xi squared minus xi is equal to 0. These are the Boolean axioms. You want to force the solutions to be Boolean. And xi times xj is 0 if is not an edge. Finally, you want a condition on the size of the clique. Okay. So if this system of equations is feasible, if and only if the graph has a clique of size k. Okay. And what we would like to show now as our main theorem to get a Lasserre lower bound is that there is no PS positive Stellensatz refutation of this system of equations of certain degree if the graph is random, drawn from G n half.
Again, can you repeat this?
So we want to show that there exists no positive Stellensatz refutations of a certain degree for this system of equations when the graph G is from G n half. So how do you show that such identities do not exist? So you exhibit a certificate. So showing non-existence of refutations. How do you do it? You just show, you build a map, a linear map from polynomials of degree less than or equal to r to reals. It's a linear mapping from polynomials to reals such that it has to satisfy three conditions. So if you want to show non-existence of degree r refutations, then you want the map evaluated on anything in the ideal of degree at most 2r to be 0. Okay, it should be non-trivial. So let me just say m of 1 is 1, and finally, this is the most important condition. m of h squared should be non-negative if degree of h is at most r. Okay? And once you have such a linear mapping, it's easy to show it. It follows immediately that there cannot exist such refutations. You'll apply m on both sides, you'd get 0 here and something non-negative, positive here. Okay? And if you're coming from the Lasserre rule, this m exactly corresponds to a good fractional solution. How do you show the existence of this m? And most often, if you start with these equations, you initially work with these two guys, and this enforces some linear constraints on what this m should be. You just try some few things, and you kind of the solution stares at you. Okay. And for us, the solution in the clique case, you just do some simple arithmetic. This is the solution you get. I'll just write this down, and I'll stop. So let me define something called degree of a vertex. So you have a graph G, and we are trying to construct this mapping M. Okay. So if I have a subset of vertices, I want to generalize the notion of degree to this subset of vertices. And the generalization we consider is the following. It's the number of cliques of size 2r I. Okay. If I is a single vertex and r is 1, the number of cliques of size 2 which contain this vertex is just the usual degree of the vertex. Right? And this is a generalization of the notion of degree. And as it turns out, you can define the mapping M as follows. You can define it just for monomials, and can define it for monomials and then extend it multilinearly to all polynomials. And you should take it to be proportional to the degree of the vertex set for that monomial by some scaling factor. Let's ignore the scaling factor, where what's important is that you get this degree. Okay? And once you have this, what you get is you have to show a certain matrix is positive semi-definite. So this satisfies this inequality, this set of constraints, this set of constraints, but the real deal is in showing that it satisfies this constraint. M of h squared is non-negative. And there you can reduce it to showing that a certain matrix is positive semi-definite. But the entries of the matrix are somewhat complicated. They depend on these degrees. Okay? And these themselves are random. But they're random in a bad way for us because they're very correlated. Okay? And that's where our the association schemes and non-commutative polynomial concentration comes in. We can use these two to show that this matrix is positive semi-definite. So even though these entries are random and they're correlated, you can characterize the correlations as a low degree polynomial and then use the theory of association schemes to estimate the variance and the expectation of this matrix. Okay?
But these matrices themselves don't come from this algebra of
No. If you look at the expectation of this matrix, which itself is a complicated object to understand, that comes from the association schemes. And the variance, again, is a bit more complicated. It takes some careful combinatorics to actually compute it. We don't compute it, but get some estimates. That also lies in the association scheme. But now we have to compare these two matrices, the expectation versus the variance. And that we do because we can compute the eigenvalues exactly. And we know which matrices are positive semi-definite. Okay, so that's where these two things tie in. So let me stop there.
So there is a strong analogy between, so I'm coming back to the very beginning, clique and so on. There is a very strong analogy between the cliques in a random graph and so on and the transitive subtournaments of tournaments. So every tournament, there is also a gap. We don't know, there is a factor of 4 between what can be said about the existence of a homogeneous subset every graph on n vertices contains either a clique or an anti-clique on a half log n, and a random it's 2 log n. And likewise, in a tournament, it's very easy to show that in an n vertex tournament there is a transitive subtournament of log n, and a random one doesn't have more than 2 log n. So I wonder, and sometimes there is an analogy, and sometimes things are easier in this domain, sometimes they're easier in that domain. Do you know? I mean, has anyone looked at the planted transitive subtournament problem? So you take a random tournament and you plant in it a larger than what you'd expect subtournament?
I don't know. It's a good question.
Hasn't, I mean,
No, I'm not aware of anything, but that's a good question.
So it's impressive. So these things. So what? How do you put? I mean, how do you put? Do you need here hypercommutativity?
Oh, here, so we kind of cheat, and we just use induction and reduce it to the degree 1 case here. So you can use induction kind of on the degree of the polynomial here.
So this can be done also for the
Yeah.
matrix case here.
Yeah,
and this is why you have to swallow this.
yeah, n to the d, yeah, exactly. And the linear case is very interesting because, I mean, it's non-trivial. It uses a it's simple, but it uses a Golden-Thompson inequality, and it's nice. So there should be some non-trivial thing going on, and we kind of push it to the linear case. So that's one open problem. Try to get this n to the d out here. And another open problem is to remove the r squared.
But would this n to the d include?
Not for us, but I think this statement itself should find other applications. I mean, it's a polynomial concentration inequality. This has had a lot of applications from the time it came out. So naturally.
Oh, you need to get 10.